Our next speaker is a .NET developer, and he's a .NET coach within his company. He helps programmers develop their career paths and make sure that they're doing everything correctly. He's the head of learning and development at Axxes Consulting, which is located in Belgium. And his name is Hannes Lowette. His presentation is entitled Actors Can Rule Your DDD World. It's all yours, Hannes. Oh, by the way, excuse me. If you have any questions for Hannes during or after the presentation, Slido, orange stage, you can write them there and then we will answer them at the end of the presentation. Sorry about that, Hannes. Now it's yours.
No problem. Thank you, John. I would have wished my first craft conference to be in person in Budapest, but unfortunately that was not in the stars this year. But I'm happy to talk to you today about using actors to build domain-driven design-inspired software systems. So what I'm going to talk to you about today is, first of all, I'm going to give you a little bit of context in the next slide, and I'm going to tell you why Actor.net would be a good choice for doing this. And then I'll dive into as many implementation details as we have time for the next 30 minutes. Now, to get all on the same page, I'm hoping that you are all a little bit familiar with the concepts of domain-driven design. But if we start implementing the concepts from Eric Evans's book, a book that was very heavily inspired by object-oriented systems, we see that in the DDD world today, we see a shift towards concepts such as CQRS and Eventsourcing. Now, to sketch you a little bit what goes into a CQRS system is we will have a software system that has two sites, and the two sites will be separated and decoupled from each other. So on the command side, we will have a possibility to send some instructions to the system, and these commands, they will never fail. But depending on what the state of our data is at that time, those commands will trigger some events, and those events will then be handled on the read side by what we could call projectors, and they will project the event data into something that is the read storage. And in an ideal world, we will want to have every query that exists on the read side hit the database in a very, very optimized way. Now, on the right side, we could do two things. We could use a classical truth database, the way that you are probably used to programming when you build a typical .NET system with a database. And in a truth database, you're going to store the state of the data at this particular time. But you could also think of it as more of an event-sourced system, where we actually, instead of storing the state, we store all the events that led up to this state being the way that it is. So if we're going to build a system like this, why would we want to use something like an actor model? Because I know that if a lot of people think about actor systems, they think of things such as IoT, or they think of stock trading systems or gaming backends or that sort of stuff. So let me tell you a little bit why Actor.net would be a very good fit for doing this. In the DDD world, we try to model the software as close to the reality as possible. We try to use the same language for the business and for the code. And this is something that we really want to also explore. Because Actor.net is an implementation of the actor model. The research on actor models dates back all the way to the 70s. And it was first put into practice by Ericsson, a Swedish company in the 80s, to build a telco system. And they managed to get, they used it because of its resiliency. And they managed to get up to 9 nines of uptime on a code base that had 2 million lines of code, which is pretty impressive, because 9 nines means that you will have 31 milliseconds of downtime a year. Now, I don't know if you've ever built a system with that kind of uptime, but I haven't. So I think that's really, really impressive. And then it was really quiet around ActorSystems for quite a bit. And in the 2010 years, we finally see some movement in this world. And we first see Akka on the JVM, of which Akka.NET is a straight up .NET port. And that happened all pretty recently. And the reason for that is that because of the slowing down of Moore's law, where we can no longer get as much gains in single core performance anymore, we see software systems that increase their performance, hardware systems that increase their performance by having more cores. And if you want to take advantage of having more cores, you're going to need something that is able to write very efficient multi-threaded code. And that is hard to do, especially if you have to manage a thread pool yourself. And that's what these actor models are actually really, really good at, because they were built to model software after the real world, after the world of physics, where objects interact with each other. I'm sorry. So what happens there is these systems are very good at taking advantage of multi-core machines, which is what we actually want if we want more performance and if we want to get close to linear scaling. Now, what are these actor systems built off? These are actors, and the actors that we are going to build, they're actually not that complex. They are a simple class. You implement them in a class that inherits from one of the Akka packages. And what you'll have is a class that has its own state, which are just properties or fields. You'll have behavior, and behavior is just a fancy word for functions or code. And then you'll have an inbox, which is the only way that you can actually talk to one of these actors is by sending a message to this inbox. And the powerful thing is that these messages are processed one at a time in order. And this is very powerful because they are, you are sure that there's only one thread that's going to run on this actor at the same time. So you don't have to implement any locking or any complex stuff to make sure that your code is thread safe, because there is no other way to access this actor than through the inbox. So you'll have this guaranteed single threaded guarantee that's running on your actor, which is extremely powerful and makes it convenient to write this multi-threaded code. So if you would do that in code, it looks something like this. This is the simplest one that you could possibly make. You inherit from untyped actor, and every message that is sent to the inbox of this actor is going to hit the onReceive method. And then you can check what type of message you're getting and decide to handle that in just some functions that you just write as you would in any other .NET class. Now, a little bit more about these messages. Also, the messages, they are simple CLR objects. And the best thing is to make them immutable. Now, in the later versions of C#, we have gotten things like record types, which are perfect for implementing messages. You have to keep into account that a message might cross a machine boundary. So that means that it might get serialized and deserialized. And therefore, that immutability comes in pretty handy. You could manipulate a message while it's being processed by another actor, but that would just be, would go against the philosophy of an actor system. Now, what the people from Lightband, not from Petabridge, claim, they claim that you can process around 50 million messages per second on a single server. On my 5-year-old laptop, I can get well over 4 million per second, so I have no reasons to doubt these claims. So the overhead of sending messages and also the memory overhead of having an actor, a single actor will cause a memory overhead of around 400 bytes in a release build. That is nothing. You can have millions of actors on a single machine and it's not going to affect your memory significantly. Now, to tie everything together, we're going to need an actor system. And the actor system is a little bit like your puppet master that keeps everything alive. This actor system will manage the actor life cycles. It will spin your actors up. It will manage their inboxes. It will handle the messaging between them. It will do the thread scheduling for us, which is the hardest part, really. And it will also manage some kind of event bus that you can use to do pub/sub messaging between actors. For reference, this is an album cover from when I was young, so that should make you able to like guesstimate my age. Now, how do you create an actor system? It is quite straightforward. If you call the factory method on the ActorSystem class that is provided by the ACA package, you're going to get an actor system back and it's going to be running. All you need to do is give it a name. Now, the tricky part is when we start creating actors, because as I told you, there's only one way to communicate to an actor. So we have no control over instantiating or deleting an actor from memory. So what we'll do is we'll create props. And if I have to explain to you what props are, the best way to actually explain this is to say that this is a constructor pointer. So this method, this generic method, will tell you to point at the default constructor of my actor. It takes a params array of objects, and those are maps to the constructor parameters if you would want to pass some. And then what happens is you'll tell the actor system to create an actor for you with those props. And the tricky thing is you'll never actually get a reference to the actor back. What you'll get back is an iActorRef. And this is just a simple object that allows you to talk to the actor by sending it messages like this. Now, what is important to realize is this iActorRef, it keeps existing even if for some reason the actor system decides to kill your actor and recreate it. You could still use this to talk to the actor and the messages will go to the new instance. So this is transparent. You can pass it around the network. It will talk to the correct actor. It's a very, very powerful thing. Now, actors live in a hierarchy. There's 3 actors that we always get. It's the root, the user, and the system actor. And underneath the system actor, we have all the things that are related to the event bus and thread scheduling and that sort of stuff. And under the user actor, we are going to create our own actors, the ones that we create in user space. The actor that we created on the previous slide, that would have been a top level actor and that would have lived at that A1, A2 level. And if actors create children, they come underneath in the hierarchy. And this is important because your address is defined by your position in this hierarchy. Now, how do you create children? Instead of using props and calling actor off on the actor system, you'll actually do it. I'm going to talk about receive actor in a second. You'll actually call it on the context. And the context is one of those properties that is set on an actor just before a message gets processed. The context is set, the sender is set. There's a couple of things that you can do, but calling actor off on the context, that is the way to create a child actor. And you have to remember that names have to be unique in the hierarchy. So you have to, well, not the names, the addresses have to be unique. So if you're creating a bunch of child actors with the same type, you're going to have to make sure, just like I did in this slide, to put an ID in their name. Now you see that we're not using the untyped actor anymore. We're using the receive actor. This is the strongly typed version of actors in the Aka.NET framework. So you can register event handlers for certain types of messages. And this will feel a lot more natural if you're a .NET programmer by nature. You will actually find this a lot more natural to do. So yeah, that's how actors create children. And there's a very important reason why you would want all these actors to be in a hierarchy, and that is supervision. I talked to you very briefly about that Ericsson telco system. And this is exactly why that is. If you want a system to be very resilient and self-healing, you're going to need a way to deal with failures. And failures in this case would be uncaught .NET exceptions. If a child actor throws an uncaught exception, that exception gets escalated to the parent. I also have 3 children. If I take them to the supermarket and they mess up, I'm also ultimately responsible for everything that they do. It is no different with actors. Now, there's a bunch of different actions that you can take depending on what kind of exception you get. For instance, you could resume, which basically discards the message and picks up the next one from the inbox. You could tell the actor to stop, which means you're going to destroy the inbox and destroy the ActorSystem, the actor instance, and it's going to be gone. You could restart the actor, which preserves the inbox, but it destroys the actor instance and recreates them from the props that the actor was created with, and then it will dispatch the same message again. Or you could escalate the error a little further to the next parent in line. Now you can apply this to either the failing actor or all of the child actors. That last one is useful if you have got a huge workload into many different pieces, and a single failure means that the whole workload has been invalidated. That would be a perfect time to basically kill off all the child actors because their processing is no longer useful. Now, don't kill off your own children. That is not a good idea. Now, supervision. How do you implement this? You override the supervisor strategy method. And what you have to return is a supervisor strategy. So I chose to do a 1-for-1, which will apply this to the failing child. And you can write a method that basically returns the directive that you want to have based on the exception, which you can completely inspect. So if it's something fatal to that actor, you're going to want to maybe stop. If you think you can recover from it, you're going to maybe want to restart. And if you don't know what to do anymore, you can escalate it to the parent. Now, I've talked to you a couple of times about actors being destroyed and recreated. And you would be right to think that this would also destroy the actor's state. So in some cases, you're going to want to have actors in most systems where we can actually recreate the state of an actor when it gets recreated. So for instance, if the system reboots or the software is restarted, or even just if an actor gets destroyed and recreated, we want to recover state. Now, there is a package that allows us to do that with a number of different databases, going from Azure Table Storage to classical RDBMSs to even document databases and that sort of stuff. But the whole thing works in the same way with every storage technology. You're going to have a snapshot store, you're going to have an event store. And when an actor restarts and it is a persisted actor, it will first recover the last snapshot that was stored. Then we're going to replay all the events that happened since that snapshot, and only then will this actor start processing new messages from the inbox, which you're going to want to persist again. And they are responsible for persisting their own events and their own snapshots. I'm going to show you in the next part of the presentation how this actually works. So if I look at DDD and actors, both philosophies actually talk about modeling code after reality, which is a big plus. They are both very message driven. Akka.NET has an event-sourced persistence built in, which could be very useful. And we have a publish subscribe event bus that we could use to tie the command side and the read side of our CQRS system together. So if we're going to apply all of this into code, I'm going to show you some snippets of what the elements would be that you would encounter if you start implementing this. Now, just as a disclaimer, none of this is actually production code. I've simplified a few things, and it's all about showing you what concepts and possibilities are there and that you could use when you would start using this technology on your own. Now, the first thing that I want to talk about are aggregates. If we talk about DDD systems, the aggregate is basically the basic building block for a certain contained piece of logic, right? It holds all the state and all the data that you would need to handle a certain command and to define which events would arise from that. So for my implementation, I wanted to do aggregates that have no dependencies whatsoever on Akka.NET. And I want my aggregates to not know about the underlying storage technology, which will help to have a very nice and testable code. So what I did for my aggregates in this demo is I made them adhere to this simple interface. And what I'm going to have is two methods. I'm going to have a check command method that would basically check which list of events would result from triggering a certain command, right? And this will not change the internal state of the aggregate yet. Changing the state will be done by applying the events. And this is going to be very useful. The reason that I made sure that the commands don't change the state yet is that we will only have one method that's actually going to change the state in a certain way. And this is helpful when we use these persistent actors that I just talked to you about. So the examples that I'm using today are about shipping beer, because I recently had some trouble shipping beer to friends all over Europe. I live in Belgium. We still make some of the best beers in the world. And I wanted to share them with my friends, and I found out that it was hard to do. So I thought about, when I was making the demos for this talk, I was thinking like, maybe I can use that as an example for the code that I'm going to show. So if I'm implementing an aggregate, all the state that we're going to hold is just going to be simple properties or fields inside our aggregate implementation. So this is very straightforward. I'm sure you've seen this before. Just remember that we're only going to set these with the events, right? And we're going to want to serialize all these fields when we take a snapshot, because this is state that we're going to want to recover. Now for the commands, we have that check command method. And in the check command methods, we can look at the incoming command, check what type it is, and then return the events that would result from handling this command, right? So all we're going to do with the check command method is make sure that we return the correct list of events. And then if we're playing events into our aggregates, all we're going to do is change the fields accordingly, because an event signifies that an operation has already taken place. So there's no point in checking it anymore. We just need to modify our state accordingly. The checking happens in the command side, right? This is just checking and seeing which events would come from it. And this is just playing the events to the state. Now, if we want to write unit tests for this, that becomes pretty nifty. What we're going to do is we can have a test-based class, and that allows us to test our aggregates. And what we're going to have is three methods. We're going to have a given, and given is just a bunch of events that have already happened on this aggregate before. So we can have a list of all the events that have taken place, and then we will apply them to the aggregates. And then when we trigger a command in the when method, we're going to call the check command and see what list of events we get back. And then we can have an expect to see if the list of events that resulted from our command is in fact the list of commands that we have gotten back. So the reason for doing this is to get unit tests like this. And this is basically what DDD for me where it comes in and brings a lot of value, because this is code that you can almost read together with your product owner. If they would look at this, if your domain expert would look at this, they could reason about this code. If I create a new beer shipment and I make sure that there's at least one bottle inside and I add a shipping label to it, when I try to send this beer shipment, I expect that I get the beer sent event, right? And this is powerful. These are tests that you can write together with your domain expert, and then you can implement them later on and make sure that you get whatever you want. So if we want to wrap these aggregates inside an actor, we can do that with a generic implementation. And this is where these receive persistent actors come into play, right? These are the persistent actors. And what you'll see at the top is every persistent actor needs a unique persistence ID. So what I'll do is I'll use the type of aggregate and the ID of the aggregate that will be unique across our system, and that should be perfect. We also no longer have a receive method. We now have recover methods and command methods. A recover method is an event that comes from the persistence technology. So it's coming from the database. It was previously stored and it is replayed before we actually accept anything from the inbox. The command could be the same event, but it's coming from the inbox, which means that it is new and it needs to be persisted. And that is what you see in that second line that I highlighted. If you persist something, what you'll do is you'll give it the event that needs to be persisted in the event store, and you're gonna give it the method that will actually mutate the state, right? And what you'll see is I'm getting events in, I'm getting commands in, and I'm getting a snapshot offer in, right? So what do these methods all do? If we're going to recover a snapshot, which is basically the snapshot coming from the database when the actor first starts, all we're going to do is replace our aggregate, right? We're going to cast the snapshot to the right aggregate type and replace the aggregate inside this generic actor. If we're getting events, what we're going to do is we're just going to call the apply event method on our actor. What you see underneath there is just a method for saving snapshots. So I decided to do it every 100 messages. You have full control over when and how you want to store aggregates. There is a message scheduler inside Akka.net, so you could do it hourly or daily or whatever you please, right? So this is just one of the examples that you can use. And you can see a couple of lines below this doing save snapshot. That is something that tells the ActorSystem to save your aggregate. And if we get new commands, what we're going to do is call the check command method. And for every event that we're gonna get back, we're gonna persist that event and replay it on our aggregate. And this is very powerful, because that means that if this is the only method that mutates the state, then we know that we have persisted all the events that we need to recreate that state after the actor gets recreated. So if you now have to have different actors for our generic aggregate actor, those would just be implementations of the aggregate actor base class with nothing else. Now I'm going to try and, because we have a little bit of time left, I'm going to tell you about what the hierarchy would look like if you would want to have these actors inside a bigger system, because we're going to need a little bit more than just these aggregate actors. First of all, we're going to have to look at our aggregate actors that are going to live there, right? And what we're going to have is an aggregate manager, and the responsibility of that actor is just to create aggregate actors when they are needed and give an iActorRef back to the person who requested to talk to this aggregate actor. We will have one actor for every instance of every aggregate. Now, the command router does something else. It's an actor that is going to take in all the incoming commands. It will connect through the aggregate manager to the correct aggregate actor, and it will forward those commands to the to the correct aggregates. This actor may become a bottleneck. There are solutions to it. Just remember that on an actor, you can never process more messages than a single thread on your system can handle, right? And then we have projectors, and these are our read sites for our CQRS system. On the read side, what we're going to do is take the event stream and subscribe to it and use that to mutate our read storage, right? So we will have one projector per type of message because we can only subscribe to certain message types. And we can actually use this to update our read storage. You can use whatever storage technology you want. You could use even an ORM inside your actors if that is what you want to do. And sometimes we need to fold events back into our aggregates. I'm not going to go into too much detail on that today. What I do want to show you is how we connect the two sites to each other. For instance, the publish subscribe mechanism. Inside an actor, you can go to context.system.eventstream and publish messages. You can do this from your actors, but if you have a reference to the actor system itself, you can also publish to the event stream from the outside. If you want to have actors that subscribe to these events, a common thing to do would be to override the pre-start method, which gets called before any messages get accepted from the inbox, and use that to subscribe yourself to a certain type of message. We cannot filter on the properties of the events in the event bus. That's why I said it would be better to have one projector per type of event, because you're going to get all the messages that are the same type of object. And to solve that bottleneck on the command router, there is something called pools and groups, which will basically use a number of identical actors and make them respond to the same inbox. The code that you see on the right is basically to create a round-robin pool with 5 identical command routers. And what you will be able to do is you'll have a single inbox that can be processed on 5 different threads because you have 5 different actors actually doing the work. So if you need these to solve these bottlenecks of actors that have an overflowing inbox, this is a perfect solution to do it. You're gonna want to maybe think about how you can shard your commands across the different routees. There's a whole bunch of different routing strategies that you can use for that. I think those were the most important parts. It's time to wrap up because we're running out of time. So what I want you to remember from this presentation is that if you're gonna use actors to build a CQRS system or to apply DDD, is that your aggregates will be held inside actors. If you want to do projections, you will do that with actors. If you want to send commands, these will be messages, and events will be messages as well. And the whole event sourcing system is actually already built in. So you could say that domain-driven design and Akka.NET are a really good match for building software. There's a bunch of things that we didn't talk about. For instance, you might want to publish part of your event stream back to the UI using SignalR, for instance. That is definitely possible. I just didn't include it in this presentation. If you want to configure ActorSystems, you're going to need to use a language called HOCON, which stands for Human Optimized Configuration Object Notation. It looks like JSON, but it's not JSON, so that's right what we needed, right? Another configuration language. But it's pretty straightforward, and you can use that to, for instance, configure these routers and pools from a config file instead of doing it from code, which makes it more flexible. You don't have to rebuild the software if you want to change something. I also didn't talk about clustering, but ActorSystems are particularly well suited to run across multiple instances, multiple machines, across a very large cluster of instances, and it scales pretty much linearly, which is extremely powerful if you want to deal with changing workloads. Of course, you're going to want to log things, and if you want to monitor what's going on in a production system, this is the only paid component in the Akka ecosystem. It is Phobos. It is built by Petabridge, the company that maintains and supports AK.net on the .NET ecosystem. It is about a €4,000 a year license. If you want to do anything meaningful with this and build a seriously scaled system, that is money that you're going to want to spend. The rest of it is open source and free, so you don't need this to get going. My name is Hannes. I am the head of learning and development at a company called Axxes in Belgium. If you want to get in touch after this talk, this is my Twitter handle and my ICQ number. I'm trying to make ICQ great again. Thank you very much for listening to this talk. And we have about 8 more minutes to answer questions. So I'm going to ask John if any have already been posted in Slido.
Thank you, Hannes, first of all, for this great speech. I'm not a programmer, but I loved your comparing software coding to Metallica. That was a first for me. I have never heard that before, but I loved it. And
I do build hobby, so there's that. So
okay. And the other thing that struck me is beer shipment applications. If you can create an actor that can send me beer, I'm going to be the happiest person in the world.
I learned from experience that sending beers is harder than I thought it would be. Apparently, if anything tries to leave the EU and it contains alcohol, you're not going to have a good time.
Okay, I'm inside the EU, so we'll talk about that.
That will help a lot.
We'll talk about that later. You do have a question, and I'm going to read it to you as is because I don't understand programming language, so I don't want to correct anybody here. Dominique asks, if I have so many events so that I need multiple handlers to cope with the load, is Akka creating multiple actors by itself, or do I have to instantiate them myself?
Oh, you mean like instantiating the I think he's maybe referring to the router pools that I talked about. There are two ways of doing it, and that is the difference between a group and a pool. In a pool, the ActorSystem will create the routees for you, so you don't have to do anything. In a group, you are free to create the members of your routing group yourself. And then all the ActorSystem will do is distribute the messages across the instances that you created yourself. Now, it feels maybe a little bit counterproductive to send around a lot of messages and to create a lot of instances of actors if you want to process large workloads. Now, know that this is not the same as sending a message across, for instance, a queuing technology like RabbitMQ or whatever. Because if you queue a message on a RabbitMQ queue, what will happen is you'll have to go across the network to get to the queue, and then the consumer also needs to go across the message. Now, everything that happens inside an ActorSystem node will basically be passing around object references inside the same process. That is how they get these amazing throughputs. And it's really not that big of a burden to pass around a message inside an ActorSystem unless you are going to cross machine boundaries. But this is something that you'll usually model when you are designing your actor hierarchies. You will do the sharding in a way so that most messages will go to a single node and do all the processing on that node. I hope that I've answered all the things that you wanted to know in your question.
Dominique replies, thank you for the reply. Great talk. And you got a big smiley face from him.
Thank you so much, Dominique.
Okay. I don't see any other questions at this point in time. So anybody out there, if you still have questions or thoughts that you'd like to share with Hannes, I'm sure you can get in touch with him on his Twitter handle or anywhere else. So
what I'll do is I'll log into the hop-in system for a bit in 5 minutes or so. So if you see me online there and you have more questions, feel free to poke me. We'll open up a video chat and we can talk more.
Okay, super, great. Thank you very much, Hannes, for participating in this conference. You made it
It was
that
lovely.
much better for us all.
Thank you, John, and have a nice day, everyone. I hope you have a fantastic conference.
Okay, thank you. Bye-bye.
Bye-bye.